Okay, now that we have a reasonable overview of the course, I want to talk about the anatomy of a programming language. Anatomy of a programming language. So linguists, when they talk about languages, they typically break it down into two separate ideas, the syntax and the semantics. The syntax is the words of our language and valid sentences according to grammar rules. So this is something like if you say that all English languages should be subject, verb, object, like Tim walks the book, right? This is a valid sentence according to subject, verb, object, as Tim is the subject, walks is the verb, and the thing he walks is the book. Now, whether or not this actually has any meaning to it depends on the listener, right? But the idea that it's a valid sentence in our language, maybe not a meaningful one, is the key to syntax, right? It's just what are the possible words and how can we combine them together into sentences that follow our standard grammar. Semantics is the meaning of sentences. So if I were to take this sentence in and try to parse it to figure out what did they mean, that's part of the semantics. Now in programming languages, there's two forms of syntax. There's a concrete syntax and an abstract syntax. The concrete is the one that you're probably most familiar with. It's what you type into a text editor when you write code, and it's the human readable form. So we'll be writing a language called Lettuce that will let us do things like this. So let x equal 10 in x plus 15. So we have a variable assignment that sets the string x to be referring to the number 10, and then in this expression here, x plus 15, we have to do a bit of lookup to find out what did we assign to x, and then we add that to 15. So this whole thing will return 25. You could also think of it like in Python, we might have variable x is equal to 10, and then we just return x plus 15. Over on the abstract side, this is the computer readable form. This lets us be able to sort of take this maybe ambiguous human readable form and turn it into something that a computer can eat and spit back up easily, right? So what this will look like is something like this. So we'll have let x constant of 10, comma, plus ident of x, comma, const of 15, and then end parentheses on, let's see, one more. So what it is a bunch of nested statements with keywords that express what that nested statement is, right? And we can really see that there's a parallel here. We have let, we have x is the left-hand side there. The second parameter is the right-hand side here. Const, we wrap around any actual numbers because, again, this is just the pure abstract syntax. These words have no meaning. They're just placeholders, which, I mean, obviously we want this to be referring to a number. But in this world, it's just right now just something called a const. And then we have plus ident of x. That's going to be looking up what is x referred to. And then const of 15 over here. So this forms what's called an abstract syntax tree or abstract grammar tree. Right, we have like let up here, and then we have a const 10 over here, and a plus, and an ident, and a const. Right, and of course, if you've paid enough attention in your computer science courses, you know that trees are great for computation. It's very easy for a computer to walk its way through a tree, usually using recursion, which we'll be doing a bunch in this class. But this is sort of the handier form that isn't broken down graphically like this, but it nonetheless has the same tree structure. And to talk about this, right, we need to make up some sort of abstract grammar which defines what are these words and how can we make these sentences out of it. So in our case, this will be something called an expression. This is actually everything in lettuce is going to be an expression. And we have this arrow that points out that if you see an expression, then it could be of one of these various forms. So it could be, say, an ident with a string inside. We see this with right here, right, which we're looking up x, and we want to know, is this a variable? And if so, give me the value of that variable. It could be a const with a double inside. Right, so this is going to refer to a number, but it should just be some sort of constant number. It could be something more complicated like plus of E1 and E2, where E1 and E2 are both expressions, so they could be arbitrarily complex. But we know that hopefully they will resolve to a number each side, and then we'll be able to add those two numbers together. At least that's the intent of writing down plus with two expressions, right? That's our intended meaning. Right now all it is some set of letters and then a parentheses with two separate expressions in it. We'll also have multiplication, division, subtraction, all the basic things. We'll have like greater than or equals between two expressions. We'll have function definitions. The more interesting thing here is the let definition, which takes in a string, the name of the variable we want to assign to, takes a expression here, E1. That's going to be the right-hand side of the equal sign, and then I'll take another expression, E2, which is the body of the rest of the program after this in statement. And there's going to be a bunch of these, and we're going to just be adding to this grammar list as our class goes on. So this is the abstract grammar that we'll be slowly expanding, and then this is the concrete grammar that we end up working with when we type stuff into a text editor. The transformation from this to this is done by what's called a parser. And this is actually takes a few weeks to fully describe, so we're going to spend half of a class on it just to sort of go through what does a parser do, basically, and what are some of the difficulties of parsers, which is why it would take so long to understand. Typically a class on compilers will handle talking about a parser. But it takes this human readable form and turns it into this computer readable form. So once we have a sentence like this in a computer readable form, what do we want to do? Well, we want to interpret it or evaluate it. And this is done by an interpreter, and we're going to be spending most of our times over on the interpreter side. So what does that mean? It means that we have to have rules that say, when I see something like plus of ident x and const 15, what do I do? What does that mean to me, right? So we'll be seeing a lot of this. We're going to have a function called eval, and we want to define what does it do when I see a plus of E1 and E2 in some local environment. The environment keeps track of all of our definitions, our variable definitions. And we're going to write this up in what's called big step semantics. Call that because we have this giant line here that sort of creates a big step. And this is from classic logic, and essentially the top part is if all of this stuff holds true, then this statement is true. But the way we're mostly going to see this is we're going to look in the bottom left corner, and we're going to see, I want to know what does eval do on this input. Well, to know what that is, right, ideally I want to add up whatever E1 evaluates to and whatever E2 evaluates to. Well, okay, so what do I need to do to calculate this? I need to eval E1 under the environment, and that should hopefully resolve to some value v1, which hopefully will be a real number. And we'll eval E2 under the environment, and that should also be a number. Let's call it v2. And if we know that both the left-hand side and the right-hand side evaluate to numbers, which we've called v1 and v2, then eval of the plus of those two should be, well, v1 plus v2. And so, yeah, the way I like to read this is I'm defining this bottom left corner. I need to calculate this the top of this step, and then the answer goes in the bottom right. And we're going to, throughout this course, what we're essentially going to do is for each one of those topics I came across, we're going to talk about which version we're going to implement in our language. We're going to add the necessary words and grammar structures that will make that doable in our language. And then we will add the evaluation rules that say exactly how do we do that. And we'll implement all of this in Scala. So we'll do this first usually on the board, and then we'll sit down with a Jupyter notebook and walk through exactly how do we implement this in Scala. Which, to do that, yeah, we need to understand how do we implement an abstract grammar in Scala so that we can write sentences like this in the least painful way, right? And then how do we make an eval function like this that can take in a whole bunch of these rules and be able to properly do this, right? As you see from this, we'll probably need recursion because we are calling eval again on two sub-expressions of this expression. And so we're going to be doing a lot of recursion. We're going to learn how to basically do functional programming in Scala using just recursion and learn how to do what are called domain-specific languages. In Scala. But I wanted to give you this overview because when we get back to this in 2 or 3 weeks, I don't want you to be confused about what is an abstract grammar and what are these big step semantics going on. Anyways, let's get into Scala.